So we continue working on the explicit scheme, and we want to study the scheme. To study a scheme, we should study the stability of the solution. The stability of the solution means that does the solution goes to infinity somewhere or not. So if your function is like this, the sorry, is if your exact function, it goes like this, and if the approximation will follow like this, okay, the question is there somewhere where the function, the approximation function, will no more, uh, if you want, bend to follow the red exact function? Is there a place where the function will diverge to infinity, even though your exact function does not go to infinity? This is the question. If so, then the solution is not stable. Stable means we will not have this kind of behavior. The function will continue to follow the approximation will continue to follow the exact function. Okay. Study the convergence of the approximation solution. So, am I convergent to the solution? And if I take very small steps in delta x and delta t, will I go further and further closer to the exact solution? And study the convergence rate to see if I'm converging fast or not. Okay, so these points are all they all concern the study of the scheme. So the explicit scheme we will be using, and you will memorize this scheme very well. So it's an explicit scheme for time, for the variable time, and this approximation for the variable in x, which we already discussed in the last video. It's a centered approximation with a step size of delta x over 2. So to do this study, we will define what we call the consistency error. What's the consistency error? The consistency error of a scheme is the error resulting from the replacement of the exact equation by the discretized equation, the discretization. Okay, so it's the difference between the discretized form and the continuous form. That's why we defined as being the difference between this term, which is f of Tn xj, which is equal, this term is equal to the derivative in time of u, of course at Tn xj, plus the second derivative in x of u at Tn xj. Okay, so it's the difference between this term and this one, which means it's the sum of the differences between, first, the discretization in time and the derivative in time, and the discretization in space and the derivative in space. This difference is the consistency error. In other words, the consistency error, if we want to look to it, if you want, in another way, let's take a simple differential equation problem where we have the exact solution and then the approximations, which are the point 1, the point 2, the point 3, etc., the point 4. The consistency error, it's like the error between doing a derivative, which is the exact one, and the approximation derivative, so the straight line which is in here. And it's at a point Tn xj. It means that if we are at this point, okay, and the approximation function in red is like this, okay, if we are at this point, what would be the difference if we, from this point and further, if we use at this point, if we consider at this point that the derivative is the exact one, which is maybe at this point it's like this. If we consider this kind of derivative to do our step, okay, let me change this point just to have something interesting. Okay, so what would be the difference if we use this green direction as our direction since it's the exact derivative, or if we use this blue direction as our direction. What would be this difference, this error between both? This is the consistency error. It means that if we are at a given step, if we want to move to the next step, but if we consider that we are at a good point or we are at an exact point, what would be the error for the step that is coming? Okay, so it's not a it's not a accumulated error from the beginning. It's step by step. At each step, what would be the error if we go further using the exact derivative, or if we go further using the approximation derivative, the approximated derivative? Okay, so we can prove for our problem that the consistency error in here in the proposition 4.2, okay, the maximum for n going from 0 to n minus 1, because the consistency error that we had, it's for n and j. Okay, so we suppose that for a given the biggest value between all the times in the norm infinity in space, it's less than c delta t plus delta x squared, which means that it's first order in time and second order in space. Okay, so if we cut our delta t in half, the consistency error with respect to time will go not in half, but the part that depends on time will go in half, will be divided by 2. And if we divided delta x by 2, the error in the consistency error, the part that belongs to the space-time or that depends on the space-time, will be divided by 4 because it's a second order scheme. So to make the calculation or to make the proof of this proposition, we will proceed by a method that will be used widely in all the exercises that we will be doing. So I will look to the method with you, and then you will try to do it yourselves alone so you can practice it, because we will be using it in the exercises. Okay. So first we will evaluate. If you look at the consistency error, I said it's two parts. It's this part minus delta t u, and then the other part, okay, the other part in here, minus delta x x u. So we'll try to find estimates for both parts alone, and then we'll combine them. So for the first part, we have this. We have to evaluate this difference. Okay, to do so, we always try to write a Taylor expansion of utn plus 1 function of t. So we suppose that we are at a point t n, and then we calculate the Taylor expansion where h in the Taylor expansion is tn plus 1 minus tn. So from the Taylor expansion, we can write that there exists a tau that belongs to the interval tn plus 1, such that utn plus 1 is utn plus the step times derivative, step squared over 2 factorial 2 times second derivative at tau. Okay, we bring u of tn xj to this side, and we divide by delta t, so minus dtu is equal to this term. Again, let's evaluate this part, which is, sorry, it's the whole part, okay, which is the space approximation. There exists y that belongs to xj plus 1, so we are calculating or writing the Taylor expansion between xj and xj plus 1. So we have utn xj plus 1 is utn xj plus delta x derivative plus delta x squared over 2 second derivative plus delta x3 over 6 factorial 3 third derivative plus the fourth derivative. So you might ask me, why are we going in time for the second order and in space for the fourth order? We will see a bit later. Okay, and then we will calculate also. So we calculate the Taylor expansion of u of tn xj plus 1, this first term in here, and then of u of tn xj minus 1, this last term in here, and we keep the middle term u of tn xj as it is, because it will be cancelled when we do the sum between all the Taylor expansions. Okay, so we can do Otherwise, we can calculate Taylor expansions of the first two terms, and then we keep the third one, etc. We can make other expansions, but we should do the thing that will give the best result. So now this is what gives the best result. Later on, we'll discuss how to know which kind of expansions or which terms should be expanded or not. So we will expand u of t n xj minus 1 over the interval xj minus 1 xj. So it's like we are doing a backward Taylor expansion. It will be the value of the function at the point xj minus it's a step size of minus delta x times the derivative, second order times second derivative, third order third derivative, and the fourth. Okay, and we combine everybody. So this is what we obtain. So this is why we went to the fourth order, because when we combine all the terms, we'll have the u of tn xj that will be cancelled with the 2un tn xj in here. And then all the odd terms in this case will be cancelled by each other. And the second order term will remain, okay, to be cancelled with the delta 2 tt u of tn xj in here. And then, sorry, it's a small error here. This is not tt, this is xx. Okay, so will be cancelled with this delta 2xx. And then that's why we need to go the fourth order, so we have some terms that are left. So we are left with this kind of terms. Now we will try to write the whole consistency error. So the consistency error is this first difference and this second difference, and we combine both to obtain. So finally we are left with delta t and delta x. This is a typing error. I think this is a squared in here. Let me check a bit in the page before. Yeah, exactly. This was a square here and not power 4. It's a typing mistake, because when we divide it by delta x2, it's a delta x. So this is how we are left with a first order in time and a second order in space. Okay, now if we want to combine both equations, everything that does not depend on delta t and delta x will be combined in one constant, which is the maximum of both constants. And then to write a nice final result, it will be displayed as follows. So we have a constant times delta t plus delta x squared. We say it's a first order in time and second order in space. Okay, so now if we want to go further a little bit and look at the convergence of the scheme, and to see if the error will go to 0 or not when delta t and delta x goes to 0. So we define the error, which is enj, as being unj minus u of t and xj. So it's the error at the point j xj tn. Okay, and then we can prove, and we'll do it right now, that the norm infinity of en, and when we say norm infinity, we are talking about the space L infinity in the space variable, because it's for a fixed time t equal to n. We can prove that the error in norm infinity is also less than c delta t plus delta x squared. So it's a first order in time, second order in space. But this is only when a given condition, or this is guaranteed when a given condition is applied, which is k delta t over delta x squared less than 1 over 2. And let me talk 1 minute about this condition. It's a very important condition. We call it a CFL condition. It's written in here, CFL, Coron-Friedrich-Schleri. It's a very important condition because it will give us a link or a dependency between delta t and delta x. So you cannot choose delta t and delta x independently. if you have delta x equals to something, of course kappa is a constant. If delta x is equal to 0.1, you have to replace in here and calculate the corresponding delta t that you can take. Of course, it's less than half. It's not equal to half. It's not equals to half. So it means that you can take delta t less than a given value. Okay. So if delta x equals to 0.1, you calculate the higher time step that you can consider, so you have a convergence of the scheme. Okay, and this kind of conditions is very common in this kind of problems. So to prove this result, we will take again the error en0 and enj plus 1. We can consider that this is equal to 0 because these are the initial conditions, and the initial conditions we took the approximations are equal to the function, the initial function. Now for the other errors at j and n plus 1, so it's for a given point, we have, so the error is the difference between the approximation and the exact value, and the approximation can be written as all this from the discretized form that we have in here. Let me show you. It's the formula that I said that you will know it very good. It's the one in here. Okay, so from this form we can write down ujn plus 1 function of everybody else, and if we do so, you will have this expression in here. So, and then here we subtract and add this term intentionally, so we can have the consistency error in here. Okay, then the difference between, or the aim is not to have the consistency error, the aim is to have this term in fact, but we will obtain the consistency error. Now the difference between this term and this one is the error at the step tn for x equal xj, which is en xj. Okay, then this part in here will remain in here, and the delta ftn xn is in here, and then the consistency error in here will give this expression. This is the expression of the consistency error. I mean, this is what you obtain if you isolate u of tn plus 1 xj minus u of tn xj in the consistency error. This can be written as function of the consistency error. I know I said before this is the consistency error in here, but I mean this can be written as function of the consistency error. That will be like this. Okay, so again I go back to the consistency error so we can see what do I mean by this. This is the expression of the consistency error. So if you want to isolate, let me clear things a bit in here. Okay, so if you will isolate this term, it will be equal to delta t rnj minus or plus kappa over delta x squared times delta t times all this term plus delta t f of tn xj, and this is what we wrote in this expression. Okay, so to continue, now the thing is that when we write everything like this, we will have a lot of errors, a lot of enj. I mean, if you look here, this term minus this one, it's the error at x equal xj plus 1 and t equal tn. This term minus this one is the error ejn, and this term minus this one is the error j minus 1n. Okay, so combining everybody, all the terms together, we will have all these errors, you know, and minus delta rnj. Now we need to find an estimate of all this. we need to find an upper bound. To find an upper bound of all this, we have to put a condition. We need this term to be between 0 and 1. Okay, otherwise it will not work. We will see why. So if we set this term to be between 0 and 1, it means that we have this condition. Then, calculating the absolute value of the error ejn plus 1, we put the absolute values everywhere for everybody in here, and then of course we put the maximal values or value of this term, which is the norm L infinity. So the norm L infinity of Rn will be C delta t plus delta x squared times delta t that's in here will be times delta t in here. Okay, and then all the other terms I will combine them together because the sum of the coefficients is equal to 1. Okay, if it was not the case, I can combine all coefficients and put a constant which is equal to the maximum of these elements. Okay, but now it's good that we can combine the coefficients to have a coefficient of 1. So we have the en of u infinity in here. So this infinity error, of course, if we say that the absolute value is smaller than this infinity error, or in here as well, so we can do a recursive procedure to go back. So first we can transform this absolute value into an infinity norm, saying that if the absolute value of this term is less than this upper bound, then the norm infinity is also less than this upper bound. This is trivial. And then we can go by an iterative procedure to we say that if the step en plus 1 is less than at the step en, then en is less than the step before, which is en minus 1, etc., to arrive to e0. But e0 is equal to 0 because at the initial condition we have no error, because we are considering that the approximation at this point is exactly equal to the initial condition. That's why we have this term that will be equal to 0. But when we go in this iterative procedure to arrive to e0, we are adding these errors, okay, as much as we go back. So we are going back n plus 1 steps. That's why we are adding these errors n plus 1 times. And this n plus 1 times delta t is equal to t, or n, in fact, n for all n going from 0 to n minus 1, n delta t is less than t. And if n is equal to n, بتصير if n is equal to n, then n delta t is equal to t. So the highest value that it can take is t. That's why this n plus 1 delta t here, for any n plus 1, will be upper bounded by t. And this is a mistake in here. There's no delta t in here. So we have ct times delta t plus delta x squared. Ct is a constant which gives the result of the theorem. So that's why we say that the scheme is conditionally convergent in L infinity, because it's convergent under a condition which is 2 kappa delta t over delta x squared between 0 and 1. Otherwise, we will not be able to do this algorithm. In fact, we always want these coefficients in here to be between 0 and 1. Otherwise, we will not have the convergence when we go back to the first term, which is e0 of u. Okay, so let me finish this video by these two results. If we go now to calculate the error u bar minus u in the norm L infinity of 0t times 0,1, it means that instead of calculating the error between u and between ujn and u of tn xj at a point t equal tn at a given time step, we'll calculate the global error on the whole mesh between the approximated point and the exact points. Okay, and this we can prove that it's less than c delta t delta x squared plus d delta t squared delta x squared. We can prove this kind of results, and also we can prove that we have this. In fact, if u of j n plus 1 can be written as we wrote it earlier, and this is only true when the source term is null, it means that the source term is f if f is equal to 0. From the discretized form we can write this, and then it means that we can have this kind of expression with these coefficients, and if these coefficients are all between 0 and 1, which is the case under the CFL condition, then we can say that ujn plus 1 is always bounded by the step in time before the minimal value and the maximal value of the step in time before ujn plus 1, which is t equal to n. Okay, so this is what we call the discrete maximum principle. And I will stop in here, and I will continue the remaining part in the next video.